Hello, welcome to our software development webinar series. We've got that link to today's materials in the chat area of your control panel. If you want to take a look and download those now, it'll be fine for you to follow along as Kevin presents today, or simply keep those for your reference for after the webinar. Today is the first of 3 scheduled webinars that kick off this new series, and we anticipate announcing additional webinar dates with more topics in the near future. Later on in this session, you'll be invited to rate a list of topics that you'd like to see at future events. We welcome your suggestions. So thanks again for joining us. I am very pleased to welcome today's presenter, Kevin Daly, a Wolfram software developer and a Wolfram U certified instructor. Kevin is one of our in-house experts on parallel computing in the Wolfram language. He has worked in academia and with Mathematica and the Wolfram language since version 5. His presentations today will talk about optimization on a single kernel, parallelization fundamentals for multiple kernels, and distributed parallelization for cluster environments. We'll be sharing some online resources and links with you along the way to guide you as you become more familiar with parallel computing in the Wolfram language, and we'll save some time to respond to your questions.
Well, thank you, Jamie, for that introduction on this part of the webinar series. And it does look like we have a pretty good split between those who have never used parallel computation and those who have written their own code to be run in parallel. So I will try to bring everyone together on this topic. The talk is actually organized into 3 parts, as Jamie explained. So the first part, I think everyone will find a benefit, even if you're a longtime user of the Wolfram language. You might see some tricks for speeding up your code, even just using a single kernel. And throughout the talk, I'll make sure we're all on the same page. I'll define some terms that we can all sort of agree on, at least for the duration of this talk, which will hopefully avoid some confusion. So without further ado, I'll start with this section on optimizing on a single kernel. So before we ramp up to using a distributed, say, cluster system, if your individual kernel processes are running slow to begin with, you won't get as much benefit if you distribute those slower computations to a distributed cluster environment. So if we can first optimize what these single processes are doing, then they'll run even in a more efficient manner using multiple kernels. So I'll explain in this section the differences between using do, map, table, and if you're not familiar with packed arrays, I'll introduce those. I'll show why listability is really the way to go in using kernels. And I will also mention compile if you really want to squeeze out all of the available computation in a numeric function, then compile might be worthwhile. And in general, a lot of the topics I'll be covering today are not exclusive to the Wolfram language. When you start to work in parallel, you have to start thinking in parallel. That involves memory management and other considerations. When working with just a single kernel, the main trade-offs that you have to deal with is between speed and memory. Oftentimes you can trade one for the other. So let's jump right into a property in the Wolfram language of its many functions, which is listability. So throughout the talk, you will see some hyperlinks to internal documentation or external sources. You can just click on these bolded words to bring up the documentation if you need. If anything is unfamiliar, also please send a question to the panel to see if they can pass it on to me. So listable functions, what this means is they automatically thread over lists. I think everyone is familiar with the list syntax in the Wolfram language. So if I go ahead and evaluate this function, you see that the list of ABC is now distributed over the log function. You still have the list format as the output, but it's automatically basically distributed this list structure. Another nice thing about listability is if you are dealing with arrays or vectors, basically lists or lists of lists, they will automatically thread over compatible dimensions. If you want to add a single term to a list, those single elements are replicated as needed, and so you still get this nice element-wise addition. So, and if you use more complicated functions, such as, say, this hypergeometric function, it normally does not take, or at least in its syntax, if you looked this up, it would not normally take a list as an argument. However, it does have the listable attribute. And so if I just use the first argument as a list, it'll automatically distribute over the hypergeometric function according to that listed parameter. So this is basically how listability works. Now let's explain which functions are listable. It's basically the numeric functions. So if we go ahead and basically query the Wolfram language using the Wolfram language, we can basically get a sense of how many listable functions there actually are. And so you'll see that all numeric functions are listable, but there are still a number of functions that are non-numeric. The only exceptions to numeric functions that aren't listable are sort of special ones like max and min. But otherwise, if you're working with sine, cosine, any of those types of functions you'd be familiar with in a math course, they're all listable. And if you want to see an even more extensive list of these basically 300 functions, excluding the numeric ones, there is still a number of functions that are listable, but I won't go into any of these details. You can sort of explore those at your leisure. So listability is really the way to go, but it's not the only way to go in the Wolfram language. There's many different programming paradigms. So we do support procedural programming, even though we do recommend the functional approach, which I'll explain using the map function below. Or you can use constructor functions like table, which help construct arrays. So let's go through these strengths and weaknesses of these different approaches, and I'll show you based on some repeated timings of simple operations, which ones are the most efficient in terms of speed. So I'll start by defining just a simple list of real numbers from -1,000 to 1,000, just to give us something to work with. Now, if you notice here, I am in the procedural section, actually all sections, I do use a do loop, just because I am basically repeating the same operation 1,000 times in each case, just to sort of beef up the amount of time it takes to run these calculations. So it gives an easier comparison between each method. So starting with the procedural, actually I'm going to go ahead and evaluate all of these just to get them running while I talk. So what we are doing in a procedural way, if you've ever used a non-functional language before, you basically have to define an array structure to hold your results, and then you simply iterate over those results. So in this case, I'm simply adding the list to itself. And so in this case, the average time was about 4.6 seconds doing it in a procedural approach. And you see table has already returned the answer. So the syntax of table is very similar to the do loop, except that when you iterate, it actually creates, you don't have to create a holding structure for the result. It creates it automatically. And so you see you've already shaved off a few orders of magnitude in terms of time. Now this is kind of a more verbose way of writing things. We are adding the two, we're basically taking a part of the array and adding it to itself. But there's actually a slightly more efficient way of using table where you literally iterate over the array of elements themselves. And the in this case, the I variable just stands as the placeholder for each element in that array. And it didn't, you'll see that this is actually a very efficient way to do things, and I'll explain later as to why that works. So a functional approach to doing these sort of array operations could be the map function. Mapping is a very common thing to do inside the Wolfram language and other functional languages. So if you're not familiar with this sort of pure functional notation, it's just using the slot function to indicate where you want to make the substitution. And you see I'm simply doing the same operations as I've done before, adding the two elements together. And I'm mapping this operation over all elements of the list. And you see that the map function is still more efficient than the procedural approach. It's slightly less efficient than doing the table iteration. So the last thing really takes advantage of the listability attribute that I mentioned earlier, where you can do element-wise addition across these arrays. And you see this is really beat all methods that I've shown earlier by even another order of magnitude. It doesn't matter if you are adding the two lists together or even just doing a simple operation like multiplying across that entire list. So this is why I mentioned listability first, because if you can use listability, it's highly encouraged to do so. That's really where you can get the most speed benefits. So you have to be careful though, because if you're not careful, you can basically undo those benefits that I've mentioned previously. So just for comparison, this is an example of using listability to your advantage. And here's a couple of ways you might naively program, if you're thinking procedurally or otherwise, that actually undo this benefit, where in this case we're using table to basically iterate over something that's already listable, or in the same sense using map to map a function that's listable over elements. And you see that we've actually reduced by an order of magnitude the efficiency of this calculation. So I do see a question that I'll repeat. It says, what makes listable functions with this low-level vectorization faster than mapping? I will actually explain that a little bit later in this talk. It has to do with sort of auto-compiling that happens behind the scenes. But I'll explain that when I actually get to that point. So another thing to consider if you're using these sort of looping mechanisms is the comparison between the actual operation time versus the overhead involved. Now, what I mean by that is, let's say you're, in a procedural sense, just replacing or putting items into this list structure. But what if each individual calculation takes a long time? And I represent that sort of time just by a pause function, but in practice, these are quite large functions you might be working with. So again, just evaluating all of these because they might take some time. So let's say I'm doing something that returns an answer, but it takes a long time to compute. And in all of these cases, even procedural, using the table function or map, the operation is always the same. But if the majority of the time is spent in calculating the answer as opposed to putting it into this array structure, then it doesn't really matter which approach you take, because the majority of the time is taken up into calculating each individual element. So if we wait about 10 more seconds, you'll see that the table and map results are virtually no different. They'll again be 5 seconds, and then you see this sort of fraction of the time is the overhead in constructing those results. So really, if the time is eaten up based on the calculation itself, the individual step, then don't really worry about the actual technique of doing that calculation. Okay, so one of the reasons that under the hood the calculations are so efficient is because we use a concept called a packed array in the Wolfram language. Many functions that basically generate large lists are already using them. The downside is that these packed arrays only accept the data types that are numeric, so basically integers, reals, and complex numbers. But they have a double benefit in both memory and speed of use. So just to show you how they work in memory, so I'll explain in the next slide why this is a packed array, but you can see just by looking at the byte count of a packed array versus an unpacked array, these are identical structures. This one is effectively, if I had written it out by hand, it would not be a packed array. And you see that you save quite a bit of memory if you use a packed array. In terms of speed, I'll evaluate these. I'm basically just doing a multiplication over a packed versus non-packed array. This is both element-wise multiplication, but you see that the not packed array is slightly slower because it doesn't know exactly, it has to basically infer each data type for each element. So one of the ways that we can access packed arrays, it's not something that is hidden or anything, but basically we're going to load a special context, the developer context, and specifically it will give us access to some functions here, and I'm only accessing the ones that have the word packed in them. So I just use the needs function to access that package, and now I can basically call from packed array directly instead of having to have the developer context in front of it. So one of the useful things is to test whether or not something is a packed array. And so we can use packed array Q, one of our query functions, to do so. And the first three here are true examples. I had mentioned range on the previous slide. The reason that this ends up as a packed array is basically any array constructor. So range, constant array, random reals, these will automatically turn themselves into a packed array form. Now, ones that sort of might be a couple of gotchas is the table function. Yes, it constructs an array, but it's not necessarily a numeric array because table can basically take anything as its argument. And so in that case, even though you are just using integers here, it doesn't know that during the table construction. The other thing is if you had typed by hand, basically created that array, typing each individual element, this is also not a packed array because the list itself has a very generic structure, and the Wolfram language doesn't know necessarily that these are all integers that you've put in. And then the last example, I'm actually using an array generator called random word, but the thing is this generates an array of strings, and string is not a data type that's allowed to be a packed array. So if you've, say, created an array that is not necessarily packed, you can go ahead and pack it. You can actually go back and forth between these two forms using these developer functions. So here's an example of an array that I typed by hand, so it's not packed, but then I can use the function toPackedArray to go ahead and pack it. And this works because they are each integers. There's no mixed data types here. And so the Wolfram language can convert this into a packed array. You can go backwards, although I'm not sure why you might want to do that, just using the from packed array form. Now, what gets kind of tricky is some operations will unpack automatically, and they'll do this sort of silently behind the scenes. But if you want to know if unpacking is occurring, then you can set a system option called packed array options, unpack message goes to true. I'm going to go ahead and turn this on, and then you'll see that some of these operations will unpack. So this first operation is multiplying a real number against a packed array of integers. And this is automatically type converting all of the integers to real numbers. No unpacking occurs. This remains a packed array. Now, if I do the same thing using the imaginary number here, the capital I, this will actually unpack. And now you see the warning message occurs that it had to unpack a little bit to do this. And so the reason is this is a symbolic representation of the imaginary number. But if I also include a real version here, because complex numbers are basically a set of reals, you see that this actually does not have any unpacking. So these are just sort of hidden gotcha here. Another thing is some operations will automatically convert to packed form. So for example, if I join two lists together, one of them I've written out by hand, one of them is already a packed array, in this case of integers, then the join function will make a packed array of the combination of the two. So there is a question here, what if I have missing in the array? So we can go ahead and test that. So I'm going to create an array by hand. And then we know that this is not going to be a packed array because I created this by hand. But let's see what happens if I try and force this into being a packed array. So you see that no warning was issued, or maybe it's because I already turned the warning messages off. But you see that this, because the missing is present, this is not a array of a single data type. This is a symbolic expression here, even though it does contain other numeric entries. So now that we understand a little bit more about how packed arrays are used sort of under the hood and how you actually have access to them as well, if you want to squeeze even more numeric computation out of your results, you might consider using the compile function. Now the compile function itself is improving all the time. It was introduced quite a while ago, and we don't have enough time. I mean, this could really be a talk in and of itself. It actually is. So I have a link here to one of our online video conferences where it actually explains how the Mathematica compiler works, how you can do code generation. And if you're more interested in that, I encourage you to view that in your own time. So it actually, the Wolfram language is auto-compiling some of the expressions that you're using without you realizing it. And I'll actually show when it does that. So I'm querying another one of our system options, effectively the compile options, and I'm only looking for, I mean, there's more options here than just the ones I show, but I'm only looking for ones that contain the word length. And the reason is, these are all of the thresholds that once passed, compiling will happen automatically if possible. So all of the timing examples that I showed a few slides ago, remember that I was effectively iterating over a list over 1,000, so I was clearly beyond the threshold of all of these. So auto-compilation was actually taking place during my previous examples. And you see, it doesn't take a very long list to auto-compile. A lot of these thresholds are set at 100, and you can change these thresholds, but they've basically been chosen such that you don't notice the transition. So what's nice about auto-compiling is you don't have to think about it. You just use table, use sum or map, etc. And so long as you have a long enough list, it'll just happen behind the scenes. You'll get a fast calculation, a fast result with, no more thinking involved. There are some sort of warnings, though, that if you are trying to utilize this auto-compiling, it only works for pure functions. Remember, the ones that have the hash or are using the head function. And as a demonstration of this, I've defined two user functions, one of which is sort of a generic expression. Another one uses the pure function approach and syntax. And if I just look at a single absolute timing of these, you see that the, I didn't expect that result. The user function actually came out faster. I'm curious. It wasn't like that before. But in any case, the auto-compiling is occurring for the pure function because I am basically iterating over a range that's larger than this threshold. So the other thing to consider is that you might have noticed the apply compile threshold is set to infinity. Now the reason this is so is because apply is a bit more nuanced. It only affects list, plus, and times. So what I mean by that is if I use the shorthand version of apply, I'll actually use plus, and I say I use plus over a range of 10 integers, it'll add all of those integers together as it replaces the head from list into plus. And so it's only these operations that are actually auto-compiling. So keep that in mind. If you want to change that threshold, you really can only use it for 3 of these functions. So if you want to go past auto-compiling and actually write your own sort of compiled code using this function, the syntax is rather straightforward. We use the compile head. We have to declare our variables. So in this case, I'm declaring a local variable or an argument x, which is a real argument. And I'm indicating that it's a one-dimensional array. So the thing is, when you start to use the compile function, you might get notice that there's no actual speed up of your code, and that's because it still has to call back to the Wolfram kernel. And that's what we really want to avoid. We want this to actually occur at a much lower level. So to sort of indicate in a helpful way, we can turn on a system option that tells us whether or not the compiler has run into any issues. So this is actually a really silly result. I'm actually having compile return a string, but compile only works with numeric data types like integers and reals. So this should give a warning, and you see it does. You see that the string could not be compiled, and so it basically has to call back to the kernel because it doesn't know what to do with this expression. So if you want to actually see what's happening under the hood, you can load another package called compiled function tools. And once you've loaded that, you get access to this function called compile print. And so you can actually print your compiled function, and it looks a little bit like very old C code. But the thing to look for is main evaluate. And so again, this is a silly function that basically is returning a string, but compile doesn't know what to do with strings. And so main evaluate is the call back to the Wolfram kernel to ask for help. And these calls are very costly from these compiled functions. So you want to avoid main evaluate as much as you can. If you see it appear anywhere, then you want to figure out a way to remove it by switching to simpler functions or do loops, basically lower level programming paradigms. So when you use compile, it's not just on a single core. You can do some kind of fun things with it. On the next slide, I'll explain how you can use multiple threads. Before we do that, you can also get some advantage by having your compile functions behave as if they had the listable attribute. So normally, the arguments of your compiled functions have to match with the specified inputs. So in this case, I have 2 argument inputs. One of them has to be an array of reals of 1 dimension, and this has to be, the second argument is just a single real number, and all I'm doing is adding the 2 together. And so if I look at this compiled function, you see I get a complaint. Now this is on purpose because in the second argument, I've specified an array, but you see in the definition of the compiled function, it's expecting just a single number. Now I could get around this by mapping over this second array, but we can do also something different. We can basically turn on the runtime attribute, which is one of the available options to compile, to allow it to be listable. So the arguments don't change at all. I still just specify that this should be a single real number, the second argument. But because I've turned on the listability attribute, you'll see these 2 comparisons here. So in the first case, I am literally mapping over a range of numbers. And in the second case, I'm putting in just the array itself. And it's this function is automatically splitting this up and running the calculation in an element-wise manner. And so you see we get not quite a factor of 2 speed up between the 2 approaches. Alternatively, I could have actually made this C1, and it should have a somewhat similar timing. Yeah. So just to show you that it didn't matter about the runtime attribute between C1 and C2 when you're using the mapping approach. So The next two sections of my talk are focused on using multiple kernels, but there's a difference between using multiple kernels and multiple cores or threads on your local machine. And you can access a multi-threaded calculation when you use the compile function. So for example, you can turn on the listable runtime attribute, and you can turn on parallelization, so that goes to true, and then it will actually try and parallelize this element-wise operation, at least in this example, to run over multiple threads. So if you recall the previous slide, this is roughly the same time. I'm going to go back really quickly. So we had, 0.228 versus 0.213, so only a slight improvement over mapping. Now it's sort of hard to come up with examples that really show off this type of approach, but I'm going to try that on this lower half of the slide. So here I have sort of derived a function that has to make a choice based on the element that you're actually running over. And so I've made three versions of this function. One of them takes an array, one that expects a single argument but has the listable attribute turned on. And then the second one has both listable and parallelization turned on. Let's see if there's any difference in these timings. So it's actually not surprising that the table function did so well, because we know that the table function, which is in this first example, is already a compilable function and actually performs very well, especially when you're using the syntax of iterating directly over the array of arguments, or the array itself. Now, it's not so surprising that when you turned on the listability attribute, that it didn't perform as well. And that's because you have to consider the overhead of splitting up the input list to run in an element-wise way. So if I had come up with, say, a better toy example, we might have seen some real benefits in turning on these versions. But you do see that when run over multiple threads, there is an improvement over just running over the listable attribute, although this is still slightly slower than the table approach. Now again, these are sort of representative timings. In real-world applications, you'll most likely see speed-ups because the overhead is sort of dwarfed in comparison to the actual calculations. So other considerations in sort of speeding up your single kernel calculations. One concept of memoization, where you basically save the value that you've calculated in order to access it much quicker at a later time. So I'm going to go ahead and evaluate these. Now I have defined a function here, ff, which using again the pause function as a sort of a representation of an evaluation that takes a long time to finish, but does return just a simple result. And so the memoization technique is you see that I'm using both setDelayed to define the function, and then I'm using just the set function here to basically recall this value. And so you see the first time that I run this using this table function, it takes about 5 seconds because every operation takes half a second and I'm operating 10 times. And then the second time I ask for it, you see it's much faster. And that's because if you actually look at the saved definitions of this function, as it's been computed, it's actually saved all of their results. And so you see that the first 10 results have been calculated, but the original definition is still present. So if you were to do ff of 11, for example, it might take a while, but it would also remember that value for future calculations. So this is one of those trade-offs between memory and speed. This definitely does take more memory to save the results. I mean, small integers like this, it's not a big hit at all. But if your results get more and more complex, you could be consuming much more memory than you have available. So other considerations for speed versus memory. If you are a bit more limited on memory than you are on speed, then you might consider a couple of things to offset the memory usage. One of them is a variable called history length. Now, what history length is doing, actually I'll just explain it here. If you do a calculation, you notice that it has both input and output labels on them. And you see the syntax, it looks very similar to basically setting values, and that's because it is. Under the hood, you can access these variables at later times. So if I run in of 83, it's actually running this exact calculation a second time. And so by setting history length equal to 0 or some very small number, these in and out variables will be forgotten. They won't actually be recorded. And this can be very helpful if you're saving large data structures within your notebook itself. Those data structures will actually be saved in these in and out cells or in and out structures as well. So history length to 0, it only saves it to the variable and not to these in and out structures. Another thing you might want to do is consider moving away from the notebook interface completely. And so you can do that by making Wolfram Language packages. So I'll go ahead and show. We have a very nice package editor. If you go to File, New, you can then find the package extension here. And that'll open up a new, it looks like the notebook interface because it still is, but these are very special files in that if you put in function definitions, I'll make this a little bigger, it types more like just a generic text editor in the sense that spaces and tabs are represented very nicely here. And so if I then save this file, and I'll go ahead and save it to the desktop real quick. So if I were to open this with just a simple text editor, you'll see that it looks very different than if you had done this opening up a Mathematica notebook. Let's see, where did you go? There we are. And so you see it has some very nice special sort of comment sections, but then you see you get basically a one-to-one sort of view of this. It's just a simple text file, easy to read. You can further edit it in a simple text editor. But again, because notebooks have a tendency to sort of grow in size as you use them because they save input and output cells, the package structure does not do that. So if I go ahead and open up this package again, so what I mean by that is if I do, oops, if I insert a new cell that is just an input cell, you can still evaluate inside this package editor. And so you can still test your code while working in the package editor. But if I save this and then again open this up in a text editor, you'll see that all of these have been commented out, all of the input cells. And so the only things that actually stick around is basically anything that you've put into a code cell. So this is a very handy thing. You get sort of the benefit of both worlds. You get sort of the benefit of using the front end notebook interface, but you also get the benefit of getting a simple text file from your results. So, and with those simpler text structure files, you can actually run Mathematica scripts. So basically, you'll see this notation later on in my talk as well. This indicates something run from the command line or a command prompt. And so math is a common way of starting a Mathematica session. But with the -script option, you can just run a simple text file, such as the one I created, and it'll just run through each of the input cells, or sorry, code cells, and evaluate sort of line by line. So this is another nice way. You don't have to start up the entire Mathematica front end. You can just run the very simple script directly through the Wolfram kernel. So just some more considerations if you are going more towards a software development approach. So other things to consider is you really have to get down to the nitty-gritty of knowing how each of your functions perform if you, again, want to squeeze more computation power out of these. So for example, you really just have to know where the bottlenecks are. And to demonstrate this, again, I'm using the pause function as a representation of a long-running function. And I actually call this slow function. And so let's say I start using these in production. So as I'm prototyping or building my code, I'll just look at a couple of absolute timings or even repeated timings as I've done before. And I'll see that in adding these two functions together, it takes a somewhat long time. And so I need to figure out, is the bottleneck in the slow function or is the bottleneck in this OK function? So then I run each of these individually, and I see that by far the slow function is taking the majority of the time. So maybe we can improve that slow function and kind of open up that the bottleneck. So again, this is sort of hand wavy. Let's say I've fixed that slow function. So in a sense, I've removed that pause as a representation of the slowness. And now when I run the slow function, you see it behaves quite nicely. So this is a way to sort of profile just within a Wolfram Language notebook. But it's not the only thing you can do. You can also profile using our Wolfram Workbench. So if you're not familiar with the Workbench, it's a product that works with the Eclipse IDE, and it lets you profile, run debuggers. It's really quite handy. It even lets you write Wolfram Language documentation pages that look as if they came from our product. So I'll only mention this now, but if you really are sort of a hardcore developer, the Workbench might be an ideal environment for you to develop your code. Personally, for my smaller projects, I use just the package editor, which is directly part of Mathematica. But again, if you're more into text editors that have a lot of nice features, the Eclipse IDE with the Workbench plugin is very nice. So that is the conclusion of the first part of this sort of three-part talk. I'll open it up to questions. At the end of each of my talks, I have this sort of glossary and references. The glossary itself, if you click on any one of these, it'll jump back to the point where they were first mentioned. And then the references that I have further down are just nice internal guide pages. So in documentation guide pages, tutorials. This is the video I mentioned about using our compiler function. And the same link I have to the Wolfram Workbench plugin. So if there are any questions, I'll take maybe about 5 minutes to answer questions before we move on to the next section. Maybe there are some questions that our organizers have flagged me to answer. So I see that one question going back to this idea of having missing data. One of the questions seems like it would be a bummer to, say get sensor data with a bunch of missing values and then it couldn't become a packed array. Well, in that sense, you just need to do some data cleanup. So if I actually had something that was missing, I'll make this bigger so we can all see it. So there's actually a very nice function now called delete missing, which will just remove anything that has a missing head in it. So if you do some data cleanup like this, you can then convert the result into a packed array. Another comment about our package format, so the .wl for Wolfram Language or .wls for Wolfram Language script. So you sort of might have seen that here as well. One of the participants has also noted that these work very well because they're simple text files that they're easy to diff and manage through Git, which I agree with. I do that, and we actually do that internally as well in the company. So another question about the Eclipse Workbench that I mentioned. Is the Eclipse Workbench integration part of Mathematica? How can I install it? If you actually follow the link that I've presented, I guess I opened it up a second time. So this describes the product, and there's this nice big red button here. Everyone likes to push big red buttons. This will actually take you to a very nice guide in how to install it, what's necessary to use it, a very nice installation guide. So hopefully that takes some of the pain out of switching over to the Eclipse IDE. So now that we've covered how to speed up a single kernel calculation, now we're going to talk about using multiple Wolfram Language kernels. And so we'll get to talk about some of these fundamental concepts. So the Wolfram kernel, sort of used behind the scenes if you use this notebook interface, is really the engine that drives all the computation. And so I need to define a couple of terms just so we sort of know how that kernel works, at least on an abstract level. And then we'll get into how we can use multiple kernels, a couple of new ways that using kernels has been introduced, this so-called task framework. And then we'll get into the more classical parallel functionality. We're actually going to focus on just using local kernels for this talk, and a little bit in using remote kernel connections, either the Grid Mathematica product or direct remote connections. So how parallel computation is sort of architectured in the Wolfram language is the hub and spoke model. So what this picture represents is the center spiky icon represents a controlling process. So basically the process that you use when you start up a Mathematica session. And all of these circled spiky icons indicate sub-processes. And you see that as this picture indicates, the sub-processes have no communication with each other. They all have to communicate through the controlling process, and then the controlling process sends any necessary signals back out to the subkernels. The way that these kernels communicate with each other is through the Wolfram Symbolic Transfer Protocol, or WSTP for short. If you've been with our product for a while, you might recall this had also been called MathLink. And it's actually the same protocol that's used to communicate from the notebook interface to the Wolfram kernel. That same protocol is used to communicate kernel to kernel, or even kernel to external programs written in C or other languages. So just to get us all on the same page, the types of processes that occur when you start up a kernel or a front-end session like the Mathematica or Wolfram desktop, you have so-called controlling front ends and controlling kernels. So these are the two you're probably most familiar with, simply because these are what happen when you start Mathematica or Wolfram desktop. The controlling front end is the notebook interface, like this presentation. And then every time you put a computation in, like 2 plus 2, and do Shift-Enter to evaluate, then that computation is running on the controlling kernel. So there are subordinate processes, and that's what we're going to sort of focus on in this talk, which we like to call subkernels and sub-front ends. Subkernels are the ones that we are really going to focus on. They are always launched as a child process of the controlling kernel, communication via WSTP. You can't run a subkernel by itself, even if you try. It'll just shut itself down if you try and launch it as an isolated event. And if you want to know how many licenses, or sorry, how many license seats you have available to you, if you look at your password, you can actually read it directly in your password. So if you're not familiar with where your password is stored, you could do system open of $password file, and that'll actually open up, and I'll do Notepad. So that'll open up the file that has your password information in it. Now, I was actually communicating with a license managed server. So in general, if you are a single use activation key for Mathematica or Wolfram Desktop, you'll see something that looks has a structure like this. And what you really want to look for is these pairs of numbers here. where the ones that I have highlighted in magenta indicate the number of controlling processes, front ends, and kernels, and then secondarily the sub-processes, so sub-kernels and sub-front ends. So this is what you're limited by. You can't launch any more than what your license allows. If you want to use more than what's listed here, then you'll need to communicate with your Wolfram sales representative in order to pay for more license seats. So why licensing is so important? I would say about 20% of the errors that Wolfram Tech Support gets based on using parallel processes is due to licensing failures. Not failure in the sense that our license technology is broken down, but in the sense that you don't have access to the license you think you do. So whenever a kernel launches, either a subkernel or a controlling kernel, it looks at that license file to see whether or not there's a seat available. Now you can actually have this file in many locations, and Mathematica will actually check different locations for this licensing file. So two of the main locations it looks in is the so-called user base directory and the base directory. And you can also access these using the system open function. And there is a licensing subfolder, and that's where, at least in my case, I have a MathPass file stored, which contains the license information. So the reason the base directory I prefer is because this is independent of user. So anyone else who logs into your machine could open Mathematica and launch kernels. But if you put your license in the user base directory, only you, your user account, can launch those kernels. So this can actually lead to some confusion, say like in an academic setting, in a large, say, computing lab. The installer might have put things into the user base directory instead of the base directory, and it looks like you haven't properly licensed them, but you just need to move its location and everything will be good. So if you're following this talk using one of our Wolfram desktop products, I just want to let you know that you might not get as much out of this section simply because you can't follow along with me and interact with the provided notebooks. That's because Wolfram desktop products don't currently allow subkernel processes. You're only allowed a single kernel. It's partly tied to the fact that you have to log in with a Wolfram ID. And there's talks in moving to a more multiple kernel approach for the desktop products. But as it is for now, you're stuck with the single kernel, the single controlling kernel. So one of the things that's also nice if you're working in a larger organization is that as a user, you don't have to think about the licensing because the system administrator has already taken care of that, like in a cluster environment. Another thing that comes up in terms of licensing is people want to sometimes use kernels on a graphics processing unit. And there's a bit of confusion. They think they need to install the kernel on every core of the GPU, and that's not true. Instead, the kernel accesses the entire GPU through our CUDA link technology or OpenCL link, and you don't need any additional licensing to use the GPU. Other places GPUs are used is in our machine learning or neural networks functionality, but that's beyond the scope of this talk. So again, any other questions about licensing, either talk to a sales associate or the tech support. So now that we have an understanding of why kernels need to be licensed and where that licensing information comes from, this picture is sort of a graphical overview of using kernels in a sort of ad hoc cluster environment. So this middle one represents your current front-end session. You might have a couple of local kernels represented by these icons, the spiky icons and circles. And you might have some kind of communication protocol with other sort of just idle computers, laptops, etc. And you can use kernels on these remote systems. Before we jump into using these sort of remote setups, let's first focus on using local kernels first. The reason is, if again, you're not using, say, the Wolfram desktop, you can follow along with me, learn everything you need to know about our parallel functionality, and then we'll come back and see how we can add external kernels to our computations. So I'll minimize this so I have access to the menu. So if you go to the evaluation menu and go to parallel kernel configuration, it'll bring up our preferences menu, and I'll try and make this a little bigger so it's easier to see. So you'll see a number of tabs sort of halfway down this preferences menu. We're going to be focusing on the local kernels section of this. So what a local kernel is, one that resides on the computer that you're working at, you're sitting at. And Mathematica automatically detects how many CPU cores you have on that machine in order to launch some local kernels. So in my case, Mathematica has automatically detected that I have 4 physical CPU cores. Now there is hyper-threading technology, either Intel's or other chips. They have sort of versions of this. These are logical divisions of the physical CPU core. We don't recommend running on them, not because you can't, but you might not get as much performance out of it because as logical CPUs go, the operating system has to basically determine how to divide the different threads up. So just to be sort of more robust, just use the physical CPU cores that Mathematica detects. I'm not saying that you can't override this detection. In this menu setting, if you switch to manual, you can then have as many kernels launch as you want, with the restriction of licensing, of course. So that's always at your disposal. So one of the ways that you can use a local one-off task, so something that sort of spins up a kernel and dies, is sort of this new task framework. I won't go into a lot of detail, but if I submit something, it submits very quickly using session submit. It runs with all of the knowledge that we have on the existing controlling kernel. And then once it finishes with its calculation, it'll come back with a result. So this is nice to just do a one-off task. You have some idea you want to run, but you don't want to inhibit your current use of the front end. Other things that you can do is local submit. Now this will actually spin up a new subkernel. So this session submit actually runs on a different WSTP connection, but it doesn't have to start anything else. Local submit starts a local subkernel to do the calculation. And there it is. So you see it took a little bit of time to spin up, and now it eventually returned the result. I'm choosing to have everything return as a message dialog just for this example. And then we also have cloud submit. So if you're connected to the Wolfram cloud, if you do a cloud submission, this will spin up a connection to the cloud. And you see the connection was successful. And then after we wait for a while, it'll also return from the cloud. Oh, sort of disappeared pretty quickly. There we go. And so you see we get the same message dialog returned to us with the correct calculation done. So this is just a way to sort of asynchronously do calculations on separate processes, either on the cloud or locally. But again, these are intended to be one-off tasks, or if you use the scheduled task framework, you can schedule when you want these to run. But this is beyond the scope of our discussion today. So let's get back into the basics of using parallel kernels in our hub and spoke model. So the easiest way to get started is either using launch kernels with an empty set of arguments, or in my case, I'm telling my local system to launch 2 subkernels. And you see I get these back. If you want to know how many kernels you currently have running, I could ask for kernels. Oh, looks like I had already started one up remotely. And then when you're all done with the kernels, you can close them manually using the close kernels function. So there are a number of functions that start with the parallel word. So parallel array, combine, etc. I won't go into all of them specifically, but I will sort of touch on how they work. So you notice that I have closed all of my kernels. If you start a parallel process without kernels available, you either will get a warning like so, or you can launch some kernels. If I hadn't already launched kernels, then this would have spun up the available kernels automatically. So for simple operations like this, due to overhead of communication, you won't notice an actual speed up, and that's one of the main sort of gotchas, is that the overhead is somewhat significant, but I'll explain how we can try and minimize that. So when you're using the WSTP protocol in this communication between kernels, you want to minimize the overhead of the communication. So you actually want to send a minimal amount of information to each kernel. The other thing to keep in mind is that each kernel, as sort of an independent entity, will duplicate any memory that you need it to access. So if you have a large matrix, for example, and you send it to another kernel because you want it to compute on just one of the rows of that matrix, don't send the entire matrix, just send the row. So really minimize the amount of data that you're sending back and forth. So because of this hub and spoke model, the types of problems that are most amenable to our parallelization scheme is the sort of embarrassingly parallelizable problem. It's the one that is completely independent of other runs of that code. So for example, I have a numerical integration that takes a somewhat long amount of time, in this case roughly a second. So if I were to do this just on a single core, this should take a little bit over 10 seconds to run. I guess it must have cached a few things. So how we first get this distributed to all of the subkernels, they're not aware of this function I've defined right away. So we should first distribute that definition, that symbol. And once we've done the distribution, we can then run these in parallel, such as, say, through parallel table. And you see that because I have 4 kernels currently running, I got roughly, not quite, the theoretical maximum, but I got a little less than a factor of 4 speed up, because these are truly operations that are completely independent of each other. So I'm going to talk about a few concepts that are not unique to the Wolfram language. One of them is memory management. So I already hinted that if you want a computation to occur on a subkernel, it already has to have the data local to that subkernel. And so it's up to you, the programmer, to try and make sure all of the data is synchronous. There are some things you can do, but the onus is on you to sort of know what the current state of each of these kernels is in. You can directly evaluate on a subkernel using the parallel evaluate function. But be careful if you do this, because you can get these kernels to become out of sync with each other. So for example, if I evaluate or set the symbol value k equal to 3, I can then separately set that. Actually, I'm going to go ahead and quit the kernel so all of my kernels are numbered from 1 to and onward again. Okay. So now I'm going to set the global variable k to 3, and then I'm going to spin up a couple of kernels. You see this is happening automatically because I haven't launched any kernels yet. Once my 4 local kernels launch, you then see that I'm saying that kernel 1 should reset the value of k to 4, kernel 2 should reset the value to 5, and then when I ask for those 3 values, you see that they're now different on each kernel. So if I were to do something like parallel evaluate, oops, missed parallel. you'll see that I get different results depending on which kernel is doing the evaluation. So this can get kind of confusing, especially when you use functions like parallel do. So make sure you have in mind your sort of data synchronicity when you're doing these parallel computations. You can use shared variables using the function setSharedVariable, but this is only useful if you access that variable infrequently. If you're changing that value every single time, like in a table or a do loop, then you're going to be swamped by the overhead of updating that variable. Because this is the hub and spoke model, every time one of the subkernels changes, it has to tell the master. The controlling kernel then has to distribute that change to all the subkernels, and if they have already subsequently changed, they have to communicate over and over and over again just to make sure that this variable is synchronized between all the subkernels. So really use this one with care, only with variables that are updated infrequently. So another sort of concept that is beyond or not exclusive to the Wolfram language is the concept of coarse versus fine-grained parallelization. It's also known as load balancing. So if I were to use a function like parallel do, it defaults to coarsest grained parallelization. So I'm going to actually quit the kernel again, just so I can have this work the way I want. So let's say we have this sort of abstract task. So I have it listed here, just abstractly pause statements representing something that takes a long time to run. So if I launch exactly two local kernels, when I use a function like parallel do, this is saying that if the iterator is less than 3, I'm going to have the longer computation. Otherwise, I'll use the shorter computation. If I look at this, the coarsest grained approach is actually splitting it up. It takes the iterator itself, which is this list of values, and because I'm using two kernels, divides it exactly in half. So the reason this whole process took 8 seconds is because the first kernel is getting hit with all of the long-running calculations, and the second kernel got the fast ones or short-running ones. So you can change this by using the finest grained method. So it's the exact same computation. I've only changed the method. And now what happens is it basically goes through the list and changes which kernel gets each operation. So now you see this only takes 5 seconds because each kernel got roughly the same amount of work. So there is a question, it's a very common question, is there any way to make the kernels communicate to each other directly instead of communicate through the master kernel? So it's funny because the short answer is no, the long answer is yes, but the reason that it seems like a contradiction is because the documented approach, the one that's supported with our lovely tech support team, does not allow communication, this automatic communication outside of the hub and spoke approach. However, if you are a WSTP guru, you can communicate between subkernels using the WSTP protocol, but you have to set up your own links between them. But we won't, that's definitely beyond the scope of this talk. So getting back to sort of this load balancing idea, there is another approach we can take, which is called parallel submit. This effectively creates your own computation queue. It's very similar to finest grained. So I'm using the table function. The reason with is here is just I want to inject the value and create different sort of abstract computations. So you see pause again is a representation of long-running processes. And you see it's quite random. So I have 10 sort of randomly long processes. So this is both difficult for the coarsest grained to do and might be difficult for finest grained in order to properly load balance. But using this computation queue and using the wait all function, I'm only using two kernels right now. And so you see the kernel that first becomes available grabs the next one in line. So if you have a bunch of short processes together, one of the kernels might just take all of them because it gets through them quicker. But this is a very nice representation of having your own computation queue. So one of the things we like to do at this company is make everything sort of easy. We want to sort of take away the difficulty of some of these concepts from the user and just have everything work. But let's say you're a little bit more nitpicking and you want to see what's going on under the hood. In our parallel framework, you can do that. So if you load the parallel package, it has a function called tracers, which will sort of show some of the communication over WSTP. One of the ones that's kind of neat to see is send receive. So what this is going to do is show anytime communication occurs between the master and the subkernels, we're going to see a message pop up. Another thing to note that the global context is rather unique, and these demonstrations will show how. So let's say I define a global variable. If I evaluate this on just the first kernel, these first two send receive messages are basically saying, hey, something has changed on the global context. We need to send that information to all of the subkernels. Then you see that the subkernels tell the controlling kernel, hey, we've got that message. Everything is ready to go. Then the parallel evaluation takes place. So first we sort of have data synchronicity with the global context, and then we send the global var to the subkernel, and you see it evaluates directly on that subkernel, but it knows what that value is because sort of behind the scenes, it was updated for us before. So this is just unique to the global variable, or the global context. If we have a function that lives, or variable that lives in some other context, and we repeat the same process, you see that there was no pre-communication. It just said, hey, subkernel 1, what is this value? And subkernel 1 says, I don't know, because you didn't tell me. And so it returns unevaluated, and then you might ask, well, then why do we still get the number 2? That's because in our effort to make things sort of effortless for the user, we silently return this symbol, and the master kernel then evaluates it. So this can sort of, the reason I like this way of debugging is otherwise you'll get these silent returns that looks like things are working correctly, where in reality, things are actually being done sequentially. They're not actually being done in parallel. And so if you ever see a symbol get sent to a kernel and returned unevaluated, you know that that definition is missing on that subkernel process. So as you get more into software development, you might start developing your own packages. Now, package development, again, there's a separate course you can sign up for. It's beyond the scope of this talk. But you'll create these packages that you want to use, and maybe the definitions you put into these packages will be useful to be run in parallel. In that case, once you have the package, you'll need to use the parallel needs function to let all of the subkernels know to use those definitions. So as an example, I'm going to create a very basic package, very, very basic. And I'm going to go ahead and store it in the base directory so all users have access to that package. Once it's there, I can call needs to get those definitions. They're just very simple addition and multiplication. In order that my subkernels also know about it, I need to do parallel needs. And once I do that, you see that some communication has occurred. The subkernels are gaining knowledge about what's in that package. And then if I call one of those functions that lives in the package, you'll see that it was evaluated directly on the subkernel. Public 2 returns 8, and then that value of 8 is sent back to the master. So this is handy, but you need to be careful once we move to a distributed sort of mindset where these packages live. You might not have access to the remote computing systems, the memory and the storage that you do locally. In that case, because the subkernels need to grab that package from somewhere, one of the sort of workarounds is to just use distribute definitions, because you can distribute entire contexts. So if I use distribute definitions of this context, it also sends those definitions to all the subkernels, including the private definitions, without the need to put this package, copy it to the remote computer's locations. This will just use WSTP to send the definitions. So now that we sort of know how parallelization works, at least sort of a very rough introduction to it, let's talk about where other kernels can come from. One of the places kernels could live is remotely, and you can just use remote kernels to access them. Now these are sort of tricky to set up, and this is external to the Wolfram language, but I'll sort of walk through this Windows system in communication with a Linux computer. So technically, any Mathematica installation can provide you with Mathematica kernels, even ones that live remotely. The thing that really hampers this approach is most often firewalls. I would say 80% of the time there's some kind of network issue between you locally and a remote server. Other things to keep in mind is that if you're using clusters, for example, you might actually be charged by the hour, or they're not even available for public use. So these are things to consider if you're trying to connect to a remote machine. So I'm going to go quickly through a couple of error messages you might see. I don't really want to focus on sort of error issues, but just to give you an idea of why this is sort of technically challenging, and it's definitely outside of the Wolfram technology stack. These are just generic networking issues that your local system administrator might be able to help you with. So the first thing to check if you're trying to talk to a remote computer is, can you reach it? And so you can use, for example, the ping function. And if it comes back that it could not find it, Mathematica is not going to, find it. So this is just a system setting. Or you might ping it and the transmission failed for some error. Again, Mathematica is not going to succeed if this doesn't succeed. Another thing you might run into if you're using the SSH protocol for communication, first you need to check if it works outside of Mathematica. So if you first SSH to a machine that you've never talked to before, it'll ask you about this RSA fingerprint. And so if you've not talked to the machine outside of Mathematica, Mathematica will actually hang on this issue. So it's usually good to SSH to each computer first. Another issue is if you put in the wrong password. Mathematica is not going to successfully connect if you get the password wrong. Another issue is just you have a very slow connection to the machine. So if the connection times out, then Mathematica is not going to succeed. And if there's a firewall in the way, if the connection was just flatly refused, you're not going to succeed. So let's say we've already completed and fixed all of those errors. Now you need to know that Mathematica is installed on each computer. So if you log into that computer and run the math command, this is assuming you're on Linux, and it comes back and says that command's not found, then you need to figure out where Mathematica is installed, if it is at all. Or if it comes back that you get access to the kernel, but it can't find a valid password, again, you need to resolve this issue, normally by licensing within the base directory. But so these are just sort of baby steps towards making this connection possible. So one of the ways that I do this from a Windows machine is I use a very small function called putty. And you want to make sure that it's actually on your computer's path. So the reason for this is Mathematica will need to access this program, and the easiest way to access it is just to have it on the path, so you can just call it without needing to know where its exact location is. So I'm going to go ahead and put in my password. So I'm going to use the run process function, and plink, putty link, is part of the putty package. And it was successful. I'm directly putting in my password, although you can't see it. And what this does is it just returns what I would expect. It's a listing of the location that I asked for. So now this is a very solid check that I can make a remote connection, because there is a computer I'm trying to log into, and I can successfully access it using the SSH protocol, which is what plink uses. So now that I know that it works, one of the things that we recommend, though, is using public-private keys so you don't have to put in such a password. And so one of the programs that I use, which again is part of this sort of low-level putty system, is, oh, Pageant's already running. So what Pageant allows you to do is actually load keys. So again, public-private keys beyond the scope of this talk. Your system administrator might be able to help you with this. But now you see I don't have the password field anymore, but it's the exact same command. And so you see the public-private keys take care of the whole password authentication. So all of this, all of these remote processes can also be taken care of in the Preferences Parallel Configuration menu. Under the Remote Kernels tab, you can actually indicate which hosts you want to go through. You can even set up the launch command directly. So Windows defaults to SSH, but I'll show you how we can change that. You can also turn on the same kind of tracers. So unlike the send receive tracer, we can turn on the mathlink tracer, and that'll tell you what mathlink is doing under the hood. But in practice, it's actually less helpful than you might think. Oftentimes, you'll just get some kind of connection generic message. So let's continue with this example of connecting to remote kernels. So I'm going to go ahead and do this on the low-level side by loading the subkernels package. And what this gives us access to is the remote command. So this is the same thing that we see in this parallel connection dialog. And so I'm going to go ahead and change that instead to use this plink program that's external to Mathematica. Everything else is the same. I'm just basically saying use this in order to basically utilize the SSH protocol. And then I can use launch kernels like I did for local machines. Now I'm going to do it for remote machines. And you see I get my kernel object back. So the connection was successful. So I know I made it look like it worked, but that's because I went through the effort of making sure all of the firewalls were open and other such nuisances. I'm actually going to turn this on real quick. I'll just show you what happens with mathlink turned on. So I'm going to go ahead and launch another kernel. And so now we get more printouts. And so you see it's opening something up. Now the thing I want you to notice is that the mathlink that was created is created on a certain port. So even though we're using SSH, which is port 22, to establish the connection, the Mathematica WSTP protocol occurs on any port greater than like 30,000. It scans for an open port number and makes the connection through that. So this is where some confusion occurs. If you have a firewall, you effectively need to open it up above a certain range of values. Otherwise, the send-receive communication will fail. And actually, the kernel would probably refuse to launch if there was some firewall in the way. So another way to access remote kernels is through our Grid Mathematica product. I won't go into as much detail about this. It's effectively Mathematica just without the documentation, but it also includes an Apache Tomcat server, which allows you to communicate through a different mechanism than SSH. So what I like about Grid Mathematica is that it can be installed, because it's like Mathematica, on any operating system. And it'll use its own protocol to communicate between them. So if you don't want to go through the rigmarole of this SSH setup, you still have to consider which ports are open. There's a very nice, guess that doesn't, there you go. So we have, again, a nice support article that teaches you how to set up Grid Mathematica, how to install it if you have access to this product. In general, you just install it on every machine. It can live side by side with existing Mathematica installations. But in general, talk to our tech support people if you want to know more about it, or a sales rep if you're interested in this product. It is also part of the preferences menu. So if you click on the Lightweight Grid tab and then click Enable Lightweight Grid, you will notice that it'll take a while to get started. That's because it's already scanning for local servers. And you see that we do have a local server set up. And if you click on that local server, you can even jump to the web page that manages those processes. But again, this is sort of beyond the scope of the talk, but it's another way to access remote kernels. Okay, so now we're going to talk specifically about cluster environments. So just to recap where we've come, we know how to optimize on a single process, a single kernel. We now know how to access basic parallel functionality. And we sort of have an idea of how we can talk to remote kernels. So this builds on the previous ones in the sense that a cluster environment is just a larger environment with more kernels involved. So if you're in academia or a government institution, you might already have access to a large computing facility. Installing Mathematica is really up to the cluster manager, the cluster administrator. But if you're interested, there are other options available to you if you aren't part of a large organization. That's more generally about cloud computing, which I'm actually not covering in this talk, either AWS, Azure, or actually one of our current partners, Rescale. So you basically pay by the hour, but it's anyone who has the financial resources can access that. So we already could talk to clusters for quite a while now using our cluster integration package, but the cluster technology has sort of outpaced our upkeep of that integration, the cluster integration package. So I'm going to show you how sort of a modern cluster approach works. And then I know I'm already short on time, but I'll try and show basically a standard way of communicating. To make sure that we're all on the same page, because I know not everybody has done cluster computing before, this diagram is sort of a rough idea of what a cluster would look like. You have a bunch of computers that are all networked together, and the network itself is connected to a so-called head node, which acts as a gateway into this computer system. The head node most likely has the firewall to protect outside intruders from accessing the compute nodes, but generally speaking, the compute nodes have free communication between each other. So normally you would connect your workstation. It might be a sort of lower level powerful laptop. And so you would connect either through Wi-Fi or Ethernet to this head node, talk to the head node, submit your jobs, and then those will get distributed to the system. So generically, how we use one of these systems with Mathematica, so oftentimes you'll use SSH because most clusters are Linux-based clusters. And so you would SSH to the head node and put in your password. And then once you're on the head node, you would use some kind of submission program to submit your job to the head node. Now, I have a sort of vague representation of what your job looks like. It's just a sequence of commands. The hash structure, so again, this is beyond the scope of the talk in the sense that the Wolfram language part of it, I will go over in more detail. But if you want to learn how to use clusters and sort of the scripting language, it's really not a Wolfram technology. So it will take a little bit of time to get up to speed. But to try and get us all on the same page, I'll explain this sort of short snippet. The first line is just indicating which program the script is running through. The second line here is telling the cluster manager, so the actual program that oversees the cluster, the software program, it's basically telling it I want to launch I want five nodes all to myself. Most systems have some kind of modular approach to the applications you have access to, and so you might use something like a module loader to load Mathematica. And then once Mathematica is loaded, you would just use it like you would in any command line environment using math and a script with a package. So once you submit a job, though, it has to wait in a queue. You're not the only one accessing these modern computation sources anymore. So you have to be patient. The job has to run on its own without any monitoring of, looking over its shoulder. And once you wait your turn, you eventually get to the top of the queue. And once you get through the queue, the cluster manager then gives you the resources you've requested. And so in this case, I asked for 5 nodes exclusively to myself. These are colored in green. And then the cluster manager just reads line by line the other parts that are in your script. So in this case, we're starting up Mathematica as indicated by an icon, the math spiky. And then the script itself, the Mathematica Wolfram language script, might spin up additional parallel subkernels and utilize them in parallel. And that's using all of the same functionality that we've seen before, using the remote kernels, using SSH to talk to each other, etc. So then once the job has finished, all of the resources are given back to the cluster, and then you can do everything again. So that's generically how you would use Mathematica in a modern cluster environment, abstractly speaking. You can still use a so-called interactive session. This is very similar to what I just described, except you need to use some kind of X Windows forwarding. The job you indicate is specifically an interactive job. You have to wait through the queue, but you notice that when you submit an interactive job, you don't get direct access back to the cluster. You sort of have to wait. But once you get through, then you actually are effectively running your job as if you had logged into that computing resource directly. So in that sense, you might run Mathematica, indicated again by the icon. And then because this is in a Windows system, or a windowing system, you get the Mathematica front end sent back to you. Now this is where the pros and cons, the trade-off here, you have to consider, because even though things are being displayed on your local laptop, for example, all of your keystrokes are being sent through the network to this remote computer. It does the calculation and sends the visual result back to you. So this can be quite slow depending on how the speeds of your network are. This Mathematica session might spin up some subkernels, and then once everything is done, you should exit your session to return all of the resources back to the cluster. So just briefly, we still have a cluster integration package. The reason this is sort of no longer encouraged to use is whenever you requested a subkernel through this method, every subkernel you asked for was a separate submission to the cluster's queue. And because they now have many, many users on them, you might wait for a very long time to get that subkernel to actually start running. Furthermore, only a subset of clusters, and not all of these are even supported anymore, or even exist. They might have been end of life. So really, we take a more modern approach, let the cluster do its own thing and just run Mathematica on that cluster. So if you need, we do have another support article that tells you in a little bit more detail than what I've gone over in this talk about how to use Mathematica in such a cluster environment. But really the main assumptions is that you have free communication, so passwordless communication between all of the compute nodes. And Mathematica has the same executable on every single file system. Generally, that's not an issue because they use cloned file systems, but just keep in mind that that is a requirement. So we've already seen sort of a generic version of the submission script. The main things to notice is how many resources you're asking for, how long you intend to run the job, and then you simply just run Mathematica as a scripted file. So this looks a bit complicated, but it's really not as different as you might think. So let's focus on just the first part here. So every cluster is different, and the approach that we take now is letting the cluster, do its own thing and just querying the cluster for the relevant information. So specifically for the Slurm cluster manager, so the simple Linux cluster manager, again, your system administrator could probably help you know what things to ask for, but you basically, scontrol is a function that is known to the Slurm cluster manager. And this is basically saying, I want to know all of the jobs, basically every computation node that was supplied to me during my request. I want to know what those are. The Slurm one is a bit trickier because you have to parse what it returns to you, which this basically says 2 nodes were given to you, and then 1 kernel per 2 more nodes were provided. So I don't want to, again, go through the details of this. But basically, once you know the names of the computers that are provided to you and how many CPU cores were provided per node, everything else is the same that we've seen before. We have a simple remote kernels command. We manually load the subkernels package, and then we simply use launch kernels using SSH to launch the kernels on every single node. So it's a bit more manual setup, but it's a more modern approach to using Mathematica on a cluster. Once this is done, you just use all of the same parallel functions that you would in a normal Mathematica script, making sure to save any results you need to an external file. So I've gone ahead and done this before. We even set up a toy cluster here at Wolfram. So I don't need X11 forwarding. So I'm using PuTTY again just to set up this connection. And I'm going to make it a little easier for us to see, bumping up the font. So this is mimicking as if I have logged into a head node of a cluster. And once you're in the head node, so as my login name is Wolfram, I can see what I have in my home directory. And I have a couple of test job scripts I've already written. The one that we're going to look at in particular is the math job here. This should look very similar to what I just showed in the Mathematica notebook. The only additional things I'm doing, I'm only asking for 1 node. But again, I'm just running a simple Mathematica script and then making sure to save my results to the current working directory. And the Mathematica script that I'm running on Slurm, this is identical to what you just saw in the code cell previously, so I'm not going to go into too much detail here. I did add additional sort of debugging. I added the Mathematica mathlink tracers, for example, but otherwise it's the same script. So on Slurm, we have the sbatch command, and so I will actually just submit the math job. And if I'm quick enough, I can actually see it in the queue. So you see the job 71 is currently running under my username, Wolfram. By the time I asked for this, it had been running for 2 seconds, and it also tells you how many or which resources it's running on. And if I look at the queue again, you see it's already done, because this is a very fast process. And then I see I actually have the result back because I asked to save this result. So if I look at, I think I can just cat the result. So this is just indicating, this is basically hello world on a cluster using Mathematica. I asked each kernel to tell me where it was located and what its local ID number was. And so you see this was able to launch 8 kernels on WTG cluster 1. So I'll leave this up in case there's any questions about this aspect. But in general, this is as far as I wanted to get today. And I appreciate your patience. We did run a little bit over. The same process is also can be done on other cluster manager systems, such as Torque. The commands might be slightly different. Again, you'll need to sort of research that on your own. But the Torque one is similar. All of these commands down here are exactly the same. It's just a little bit easier to parse for the available resources that were provided. But in any case, if you have any other questions, I'd be happy to answer them. So I did anticipate this question, so I'm glad you asked. How do we distribute big data files over a cluster? Strictly speaking, that's beyond the scope of this talk. I wasn't intending to talk about big data. I was mostly focused on speed and using kernels in distributed environments. It's not impossible to distribute big data. In general, you might use an external program such as Hadoop to do these kind of big data things. If Mathematica is installed, you can access it. I think I will just actually stop my explanation there. That's beyond the scope of this talk. Unless you meant something else by distributing big data, because recall I did talk about memory management in the scope of using kernels. Because each kernel would be, actually I'm going to go back to my main diagram. So let's say the kernels, or you have access to a cluster like this, a big memory cluster. Assuming that the files you want to process already exist on each of the nodes, then all you need to do is spin up a kernel, like I just demonstrated, use the Mathematica functionality to access the local file system, so you can actually I need to get out of. So you can use things like file names or other file type functions to access the local file structure of the local compute clusters. But this is a bit more involved.